Hello, and welcome to section 21.4, 3D equations of motion. In this video, we'll cover the generic equations of motion, and then we will apply those to an example problem, which is example 1 here. So for our equations, we'll start off with translation. Remember, our motion is generally translation plus rotation. So for translation, sum of forces equals mass times acceleration of the center of gravity. Equations that look very familiar to what we've seen in the past. You can break this up into x, y, and z. You could use other coordinate systems, but our rotation aspect has not been derived for those. When you go to find these accelerations, you're going to probably have to go back and use your kinematics from chapter 20 to find these accelerations. In rotation, we get that the sum of moments about either the center of gravity or some fixed point O. So this could be, again, an instantaneous center, or it could be an actual fixed point. It'll be the derivative of the angular momentum, either about the center point G or about point O. Now, previously this was I alpha, but now it's going to be the derivative of this because we're in 3 dimensions. When we went through kinematics, chapter 20, we had an equation that says if we want the derivative of a vector, any vector, we can break that up this way. So we have the derivative of the vector in the local coordinate system, the x, y, z, and then we have that vector. So this is the momentum vector about g, and then this is the rotation of the x, y, z coordinate system. So same thing here. If we can position x, y, and z coordinates such that our products go to 0, then we get the following equations. About the x-axis, we get ix omega x dot, so this is basically alpha x, but you're going to be careful. And then minus iy big omega z small omega y. So this is, again, rotation of the coordinate system. This is rotation within the coordinate system. And then iz omega y omega z. So again, rotation of the coordinate system about y, rotation of the body about z. And then that pattern repeats all the way down here. So this is our general form if we can constrain these to be 0. If we can't constrain them, this gets much longer. There's 3 extra terms on each of these. We can simplify it further if we constrain it such that omega is equal, lowercase omega is equal to capital omega. If we do that, and we still make sure our reference axis coincides with our principal axes, which causes these to zero out, then we get called Euler's equations. And so these are the simplest form that we get in 3 dimensions for rotation. So we still get our ix omega x dot, but now, since omega is alpha, these back terms combine, so that you get omega z, omega y, omega zy, omega z. So we would combine those, and then you get this minus quantity minus kind of thing. And if you want to distribute that minus and make this plus, you can. But this is just how the book has it written. So this is ideally what we want to use. This is our simplest equation. But if for some reason we can't get omega to equal capital omega, the rotation of the coordinate system, then we have this general form to fall back on if we can make our products go to 0. So let's look at that with example 1. So example 1 has a bar. So again, I'll show it back over here real quick. So we have a bar being held by a person sitting on a stool. They're spinning around the stool at a constant 3 radians per second, and then they are lifting this bar, trying to keep their hands in place, and they're lifting the bar at an angular acceleration of 2 radians per second squared. So I've tried to redraw this. I got a little bit messy, so I drew it again. So this is more of our free body diagram. So we have weight going down. Do not forget to add weight. This is a free body diagram. Then we have our reactions, AX, AY, AZ, and then the moment about each of those. So we have 6 total reaction forces that we've been asked to find. We've been given that we have 5 going down. We were told how to orient the axes in this case, but if we weren't, we would have wanted to choose something like this. We might have flipped which way X, Y, and Z were, but same idea. Basically all the products would zero out, which they do when we put it at 0 and we orient it this way. And again, you could flip-flop X and Y and all that kind of stuff if you wanted to. So this is our local coordinate system. at G. We have our global coordinate system over here at O. This would be kind of like, if you go back to the picture, this would be like the shoulder of the individual. We do have a point A and we do have a point B. We note that omega z, which is big omega z, because it's the rotation of the small coordinate system with respect to the big coordinate system, it is 3 radians per second. And then in the local coordinate system, we have a rotation omega x about the xyz of -2. So keep in mind that x points out this way, but it's rotating this way. So my thumb points opposite little x. So that's why I get the negative sign. So then what we want to do is we want to go try to find each of these. So let's start with our translation. So sum of forces in the x equals mass, acceleration, center of gravity in the x. Again, if you can, indicate which direction is positive for these things. So this is just going based on this coordinate system. So all I'm going to have in the x direction is the ax. The mass is going to be 5 divided by 32.2. And then agx I need to find. I'll actually have to find it for ay and az as well. So I'm going to take a slight detour over here. We're going to go find all of our accelerations. So we want to find, ultimately, ag. And so we can relate that to the acceleration of point A. So I'm going to use an equation from chapter 20, also from our planar. It looks the same. So we note that this is rigid. Our radius is not going to change in magnitude, so I can use the translating coordinate system. I don't have to use a translating and rotating. So in that case, I will get alpha crossed with, alpha vector, the vector 2g from A, and then plus omega cross omega cross rg to A. So that should look familiar. You did this with in chapter 20. So acceleration of A, I will need to find that. Alpha is just the 2 radians per second. We're going to cross that with the vector 2g from A, so that's 1.5, and it's in the negative j. So negative 1.5 j hat. And then we're going to get omega cross r, g to A. So our omega is caused by this rotation up here. So that is the omega z, so it's just the 3. So we get 3k hat plus 3k hat. And then we're going to cross that. Sorry, this is all getting really squished. Let me just rewrite this. All right, there we go. So all of that, we still have to find acceleration at A, but I have my terms here. So I'll go ahead and clean that up, and then we'll go find acceleration at A. To find acceleration of A, so basically what we're going to do is we are going to go from the shoulder to A, and then from A to G. So we're just going to do this in steps. So we're going to just have a similar set of equations for A. So acceleration of A is the acceleration of our 0 point. And then again, the guy should have a consistent length from his shoulder to his wrist, assuming he doesn't bend his elbows. So it should be a constant 2 feet there. So same equations, but again, we're going to go from the shoulder to the wrist, and then from the wrist to the center of gravity. Makes it a little bit easier to think about and do. So our shoulder does not move, so it is zeroed out. We do not have an acceleration from our shoulder to our wrist. The acceleration happens after our wrist, so there is no acceleration. So the only thing that we get is this omega cross r. So our omega is that 3 k hat due to the rotation about z. And then the shoulder is 2 feet away from the wrist, so we're going to use a -2, and it is in the j hat direction. When you do this math, you will get an 18j. Alright, so we bring this back down. And so AG then becomes 18 J hat plus 3 K hat plus 13.5 J hat for a total of 0, 31.5, and 3. So that is our acceleration of the center of gravity. Now it's pretty easy to plug all these in. So now our acceleration is 0 in the x direction, which means that AX is 0. So we have no reaction in the x direction. I can do sum of forces in the y being pointed this way, equals mass acceleration, so over 32.2, and then AGY is 31.5. In the y direction, here we have just AY. That's the only force we have in the y direction. When you total this up, you should get 4.89 pounds. All right. And then in the z direction, sum of forces in the z equal to mass. Again, mass is over 32.2. Our acceleration in the z is just 3. And it's just a coincidence that this is 3 and we have rotation of 3. That's just a coincidence. That's going to be up. In the y direction, sorry, z direction, we have weight going down. Do not forget to include weight here. And we have AZ going up. So we will have AZ minus FG equal to, and my right-hand side is 0.4658. My weight is just 5 pounds, so therefore AZ becomes 5.4. If you round it, it's 4.7, but we'll go 4.66 pounds for now. Alright. So now what we have left to do is to find the rotation. So I'm going to do that on a separate sheet of paper because we're kind of out of room here. So to find rotation, we first look at this thing and note that, again, we've put this in the center. IXY, IXZ, and IYZ are all 0. All of our products of inertia are 0. This is a solid. Basically, the radius from O to A is constant. The radius from A to G is constant. So that means that I'm getting the case where big omega equals small omega, and IXY, IXZ, and IYZ are all 0 due to symmetry. So this means we can use Euler's equations. And Euler's equations were these. So here's Euler's. So let's go ahead and figure out what we do know. So we don't know IX, IY, or IZ, so we can find those in a second. We do know that, again, we know that big omega is small omega, so we know that omega x is 0. We know that omega y is 0. And we know that omega z is 3. So what that means is we have a case where omega y is 0, so we're going to zero out that entire term. We have an omega x in this one, so we're going to zero that one out. And I have both in this case. So none of these secondary terms are going to matter in this case, because we only have angular velocity in the z direction. We do have rotation about x, but not any velocity, instantaneously at least. Alright, so now we need to go find Ix, Iy, Iz, omega x dot, omega y dot, omega z dot. So let's do that real quick. We'll do that down here and then bring stuff back up. So we have a rod about its center where this is z, and this is y, and this is x. So if I go find Iy in the back of the book, it's going to be 0 for a slender rod, because we weren't given a radius of this for this rod, so it is going to be assumed to be 0. Iz is the same thing as Ix, and this is going to be 1/12 mass length squared. So in that case, we're going to get 1/12. This is a 5-pound rod. We divide it by 32.2 to get mass, and it is 3 feet long. So when we do that, we get a total of 0.1165 feet to the 4th power, if you want to put units on that. Okay, so we'll need that. Now I need to go find my other pieces. So omega x dot, omega y dot, and omega z dot. Alright, so to find our accelerations, we use this equation. Again, we did this in chapter 20. So big omega dotted, and then local accelerations, and then velocities crossed with the rotation of the coordinate system. So the only local acceleration we have is that 2I. We have 3 for our rotation of our coordinate system, and then there's no local accelerations. If you wanted to, you could put a 3k here, but I wouldn't. I just call it a 0 vector. So either way, you're going to get nothing out of this, and then you're just going to have the 2I right here that's going to come out. So that means that we're going to have -2 for omega x dot, 0 for omega y dot, and 0 for omega z dot. I go plug in some numbers. So that means that this term is going to 0 out. That's omega z dot. This will 0 out because this is 0 and this is 0. And then we're actually going to have some terms here. So let me bring back the free body diagram. So Ix will be that 0.1165. Omega x dot will be -2. The moment's about x, so x points out this way, which means any rotation this way is positive. So I have my max about that, so I include that. All of these, ax, ay, az's, are at a, so I do not include those. Okay, so I need to make a slight correction here. So remember that all of our axes pass through G here. So our x-axis is actually passing out through G towards us this way. So I need to do all of my, so the force of gravity will actually pass through that center point G there. The moment about A will still cause something. AX will not cause any rotations about the x-axis, AY, X through there. AZ, though, will. So in an axle and a half away, it would cause a positive moment. So you could do a cross product to figure that out, but you can just manually determine the sense there. So instead of 5 here, we're going to get, so MAX, then we're going to get the 1.5, and then we're going to use AZ here instead. And AZ is 5.466 if you look at the previous answer that we got. So 5.466. And that's going to be equal to 0.1165 times -2. When you solve this for MAX, you will get a negative 8.43 pound-feet. Alright, so now, moments about the y-axis. So about the y-axis, we have this moment, we have MAY, so the y-axis is this way, which means anything acting like that, right-hand rule, will cause a positive moment. So we have the reaction at AY, gravity acts through there, Y acts through there, Z will not create any moments about the y-axis, and neither will the AX. That's the only one, and so that is just going to be equal to, so this is zeroed out because both of these terms are 0, and then we have an omega x which is 0, so we just get this as 0. And then for the z, so z points up, so anything this direction. So in the z-axis, we're going to get MAZ. Oops, let me scroll this up a little bit. scoot that up, and then I'll bring this back down here so you can see it. So we have the Z. The only thing that will create a rotation would be the AX, but the AX, if you go and look at it, was 0. And so that term will also be 0. Again, omega dot was 0, and then both of these terms are 0. So MAZ will be 0. So that means that, alright, so let's just recap what we did. So we were asked to find those reactions, AX, AY, AZ, moments about the X, Y, and Z axis at A, technically. We drew our free body diagram over here. First thing we did is we went and did sum of forces in the X, Y, and Z using our equations for translation. Our mass was 5/32.2. To find our accelerations at X, Y, and Z, we proceeded to calculate the acceleration at point A from the shoulder, and then the acceleration at point G from point A. So you can see that over here. So we just worked our way through. We noted that each one of those lengths, so the length from A, so from O to A was constant, and from G with respect to A was also constant. So we plugged in our numbers and we were good there. Because those were constant, we were able to state that big omega was equal to a small omega, and because of where we put our coordinate systems, so we put it right in the center of the bar, then our products of inertia dropped to 0 due to symmetry. That allowed us to use Euler's equations, which were these right here. We pulled our omegas in. Again, big omega equals small omega, so we pulled all of those in for omega x, y, and z. And then to find our accelerations, we used this equation. So we had our -2 for our local acceleration. We had our 3 for our rotation of our coordinate system, and then we had no other angular velocities. So we ended up with just the 2i, because this term will zero out. After plugging all of that in, most of the stuff zeroed out. So omega y dot, omega z dot, omega x, and then omega y. The only thing we had left to find was really ix. Ix we found, so again, it was at the center of the bar, so we just used a slender rod, and it was 1/12 ml squared, did the math. So we plugged that in there, and our omega x dot was -2. To get our accelerations, to get our moments, so in this case, we only had AY, in this case we only had AZ. So our most interesting case was about the x-axis. So we had the moment about A in the x direction, so the x component of that moment. So that acted in that direction. And then normally we would have used the force due to gravity of the weight, actually 1.5 away, but we wanted to be careful, and we wanted to use our local coordinate system, which was actually here at x, y, and z. So we wanted to do our moments about that x-axis. We don't actually have an x-axis over here. It's way over here. So we need to be careful and not use FG and instead use AZ. So if you use FG, you're going to put a 5 in here. If you use AZ, you're going to put the 5.47 in here. So it actually gives you different numbers. So again, that we use the AZ because we're doing moments about x, not moments about A. So it's about the axis. And so that is going to be the 1.5. We did check it for sense. We noted that it was going to go around this way. So that was positive sense. Then we did our calculations and found our answers. So hopefully that helps. If you have any questions, feel free to reach out.